today's video, we'll look at the area between curves. We've already found how to find the area underneath the curve, and this will be an extension of that. So say we have two functions where one function is above the other at all times. So f of x is above g of x in this case. What we're going to try and do is find the area between those two curves between two x values, which in this picture would be a and b. Our general strategy is just like when we found area under the curve, we're going to split it up into a bunch of tiny rectangles, and essentially we'll take the sum of those rectangles to estimate the area between the curves. Well, what will happen is we'll have our number of rectangles become very large. As our number of rectangles become large, our approximation will become better and better of the area under, or the area between the curves. So essentially we have a limit, n is our number of rectangles, then that will get infinitely large, and this is the same thing that we saw with our definite integral. So essentially what we're doing is we're just taking the definite integral of the top function f minus the bottom function g. And then here is what we get. We get our integral from a to b, where a was our starting x value, b was our finishing x value of our interval, f was our top function, g was our bottom function, and we take the integral of the difference of those two functions. That will give us the area under the curve. And again, notice underlined in blue there, this is assuming that f is greater than g. So you're doing top minus bottom. Now, if we had the case where, say, g, the bottom function, was 0, that's then essentially just the same as finding the area under the curve, which we've already been doing. So here's kind of a visual example. You got your curve f and you've got your curve g. So if you take the total area under the curve f and subtract off the total area under the curve g, that will leave you with the area that is between the curve. And that's essentially what we're doing with our definite integral of f of x minus g of x. So let's look at an example. So we want to find the area that's bounded by e of x and y equals x. So e of x, they're telling us, is the bound above, and y equals x is going to be the bound below. So let's sketch a little graph. E of x, when we plug in 0, we get back 1. And then that'll be curving upwards. Y equals x is going through points like 1, 1, 2, 2, things like that. And we want to find in between 0 and 1. So essentially, we want this space here that we're trying to find. So we'll just do our integral from 0 to 1, because that's our starting x value and our finishing x value. And we have to do the top function minus the bottom function. Well, our top function was e to the x, minus our bottom function, which was just y equals x. Now, if that second function had multiple parts, we'd have to put it in parentheses and distribute the negative, but we don't have to here. And we've got dx. So we'll take our antiderivative. E to the x's antiderivative is e to the x. We'll have minus 1/2 x to the second. And we'll be evaluating this from 0 to 1. So we'll have e to the first minus 1/2 times 1 squared minus, start a parenthesis, e to the 0 minus 1/2 times 0 squared. Now this is a case where you got to be careful and not just discount all the spots where we plugged in 0, because e to the 0 is actually going to come back as 1. So this will give us e minus 1/2 minus 1 minus 0. So in the end, we'll just get e to the e minus 3/2. Oops, halves, not thirds. Okay, and that's just coming from doing the minus 1/2 minus 1. And that is what represents the area between our two curves, e to the x and y equals x, when we're looking at the x values from 0 to 1. And here's just a little bit better visual of that, of the area we just found. So again, that area there we just found to be E minus 3/2. Now it's always helpful to sketch the region. Sometimes our two regions are going to meet at a point on one of our ends, or possibly both of our ends. If it's meeting at a point, they don't have to necessarily tell you in the question what your starting x value or possibly ending x value is, because you should be able to then set your two equations equal to each other to find where that is. So if they're going to meet at a point, they might not tell you what that x value is. You might have to find it on your own. Okay, again, this is just summarizing. We're always doing the top minus the bottom when we do our integral. And again, here's the two cases. On the left, we have coming to a point at the beginning. On the right, we are coming to the point at the end. Sometimes we might not be coming to a point on either of them, or we might be coming to a point on both ends of our area. Anywhere they come to a point, they do not have to tell you what it is necessarily. You might have to find it. So we're going to find the area of the region enclosed by x squared and y equals 2x minus x squared. So we're going to sketch a graph first. Why don't we do 2x minus x squared? That should be a parabola opening down. Two is going to be a 0 in it, because when you put in 2 for x, you get 4 minus 4. And 0 will also be a 0, meaning our maximum must be at 1. When you sub in 1, you get 2 minus 1, which is just 1. So our graph will look something like this. And then our other one is y equals x squared, which will have a point at 0, 0, negative 1, 1, positive 1, 1, which will look kind of like this. So the area we want is right in here. So we'll do our integral. Now these, they cross at pretty nice points, so we can see that clearly on the graph. We don't necessarily have to set them equal. They are starting at the x value of 0 and finishing at the x value of 1. And we've got to do our top equation minus our bottom equation. Well, our top equation there is our blue one, our 2x minus x squared, minus our bottom equation, which is the x squared. So this will then give us the integral from 0 to 1 of 2x minus 2x squared. And we need our dx on the end of each of these. So we'll take our antiderivative. We'll have x to the second divide by 2, so we just get x to the second. We'll have x to the third divide by 3, so we'll have negative 2/3. And we are going to evaluate that from 0 to 1. So we'll have 1 squared minus 2/3 times 1 cubed minus, start your parenthesis, 0 squared minus 2/3 times 0 cubed. 1 squared is 1. 1 cubed is 1 times negative 2/3 is negative 2/3. And we'll have 0 for each of the others. So this will end up just giving us 1/3. So our red area there between 2x minus 2x squared and x squared is really just 1/3. And there's a little better picture of what we found. Essentially, we found lots of little rectangles, made them smaller and smaller, and we saw what that was approaching that area, and it was 1/3. Now, we might have some more complicated scenarios where graphs cross multiple times and they switch which ones are top and bottom. In that case, we would have to do separate integrals. We would do an integral for section S1 there, where we would do the integral of the red function minus the blue function. And then we would add on a different integral of the blue minus the red to find section S2. And then we would add on another integral to go back to red minus blue. So if it's switching which is top and which is bottom, you need to do separate integrals for each of those sections. And we'll look at a case like that here. So we're going to find the area of the curve, or area bounded by the curves y equals sine x and y equals cos x from 0 to pi over 2. So sine starts at 0 and goes up to 1 at pi over 2. Cos starts at 1 and goes to 0 at pi over 2. So the area we want to find is that section. And then we also want to find this section. Now, we need to be able to tell where they're crossing here. We know this is 0, the other one's pi over 2. Well, sine and cos are the same when you have a 45-degree angle, because they're both 1 over square root of 2 if you do your 45, 45, 90 triangle. Well, in radians, that's pi over 4. So when we do our first integral there, we'll be going from 0 to pi over 4. Our top function is cos, so we'll be doing cos x minus sine x dx plus, and then we'll switch over and we'll do it for the blue section, which will be going from pi over 4 to 1. And now the sine x is our top function, so we'll do sine x minus cos x dx. So our antiderivative of cos is sine. The antiderivative of negative sine is positive cos. And that's going to be evaluated from 0 to pi over 4. Our antiderivative of sine is negative cos. Our antiderivative of negative cos is negative sine. And that's going to be evaluated from pi over 4 to 1. So we'll be doing sine pi over 4 plus cos pi over 4 minus, and start a parenthesis, sine 0 plus cos 0 plus, we'll have a negative cos. Oops, I said 1 for these. Sorry, this should be pi over 2 for each of them. Not 1. So we'll have cos of pi over 2. Then we'll have minus sine of pi over 2. And then we'll have minus in parentheses. We'll have negative cos pi over 4. And then we've got a minus sine of pi over 4. So let's just off to the side, just to remind you, we've got 45, 45, 90. That's 1, 1, square root of 2. So sine of 45 is 1 over square root of 2, which we often write as square root of 2 over 2. We'll have plus another square root of 2 over 2, minus, and we'll start a parenthesis. Sine of 0 is 0, plus cos of 0, which is 1. Then we have plus a negative, so it's really just a minus. Cos of 90 is 0. Then we'll have minus sine of 90, which is 1. And then we got a minus in the parentheses here. So minus a minus would make it a plus cos. And we're doing 45, so I have square root of 2 over 2 again. And then minus, distributing to the minus sign, will again make it plus sine of 45, which is square root of 2 over 2. So here we'll have 2 square root of 2's over 2, which is just 1 square root of 2 over 2. We'll have minus 1, and another just single square root of 2. So this ends up becoming 2 square root of 2 minus 2. So what we just found is we found our area in between sine and cos from 0 to pi over 2. And again, we had to split it up because it switched which was the top and which was the bottom. So here's a little nicer picture of it. And one of the things we could have done is notice that they are symmetrical there, A1 and A2. So because they're symmetrical, we could have, if we wanted, just done it from 0 to pi over 4 and then doubled our result. We would have gotten square root of 2 minus 1, and then when we doubled it, we would have gotten 2 square root of 2 minus 2, okay, if we had noticed that ahead of time. So one last thing to talk about with these is sometimes it might be difficult to get y by itself. So it might be hard to do a top minus bottom where we're doing a integral in terms of x. It might be easier to get the function with x by itself so it's in terms of y. So we could also find our area between curves in some cases by doing a function in terms of y. And if you are doing it in terms of y, top minus bottom was done. Top was more positive. So when we do in terms of y, we'll have to do right minus left. So you either do the integral of top minus bottom if your function's in terms of x's, or right minus left if it's in terms of y's. And we're going to look at an example that deals with that. So we're going to look at y equals x minus 1, and the parabola y squared equals 2x plus 6. So if we sub in 0 for y, x would have to be negative 3. And I'm talking in this function here. If you sub negative 2 in for x, we'll get back 2. Two is equal to y squared, so we would have plus and minus square root of 2. So we'll have negative 2 square root of 2, positive 2 square root of 2. When you sub negative 1 in for x, we'll get back 4 on the right. Square root of 4 is 2, so we'll have negative 1, 2, negative 1, negative 2. When you sub in 0 for x, we'll get back 6. So that'll be square root of 6, which is somewhere around here. So that's essentially what our parabola is going to look like. It's a sideways parabola. Now x minus 1 will start at negative 1, and then we're just going up 1 and over 1 each time. So we'll look something like that. Our area that we want will be this area here. Well, notice for the first section of that, the top and bottom are the same function. And then it switches to the top being the sideways parabola and the bottom being the line. But if you look at it right to left, the right function is always the line, and the left function is always the sideways parabola. So that's why this would make more sense to do it in terms of y and to do right minus left. So for our integral, our right-hand function is y equals x minus 1. Well, we need to get x alone, so that'll be y plus 1 equals x. And that's what we'll start with. In our other function, if we get x by itself, we will have y squared minus 6 over 2. And the nicer way of writing that will be 1/2 y squared minus 3. So we'll subtract that, and it's got to be in parentheses because we're subtracting both parts. And this is going to be dy. Now we have to find the y values where these both cross. So what we can do is we know that y is equal to x minus 1. So we'll sub that in for y. So again, we're just subbing this in where y is, solving our system of equations. This will give us x squared minus 2x plus 1 equals 2x plus 6. Get everything on one side. We'll have x squared minus 4x minus 5 equals 0. We'll get x minus 5 and x plus 1. So we'll get x is 5 and x is negative 1. Well, we need to know the y values for our integral, though. So we know we have 5 comma something, and we have negative 1 comma something. Well, just sub them into this one. It's easier. 5 minus 1 is 4, and negative 1 minus 1 is negative 2. So we're doing our y values in our integral, because we're doing dy, so we'll have negative 2 to 4 for our bounds. So let's neaten this up some. We'll get minus 2 to 4, y plus 1. We'll distribute our negative. And then we can combine some like terms. So this is really negative 2 to 4, minus 1/2 y squared plus y, and then we'll have a plus 4 on the end. And now we're ready to take the antiderivative. Y squared will become a y cubed. We divide by 3, so we'll end up getting negative 1/6 out front. We'll have 1/2 y squared plus 4y, and we're going to evaluate it from negative 2 to 4. So we'll have negative 1/6 4 cubed plus 1/2 4 squared plus 4 times 4 minus and start a parenthesis. We'll have negative 1/6 times negative 2 cubed plus 1/2 times negative 2 squared plus 4 times negative 2. So this first term will give us 64 over 6, and it's negative, which reduces to negative 32 over 3. 16 and then a half will give us 8. And then 4 times 4 is 16. We'll have minus, and then in our parenthesis, we'll have negative 8 times negative 1/6, which would give us 4/3. Negative 2 squared is 4, times a half is 2. And then we'll have negative 8. And if we distribute our negative, we'll have negative 32 over 3. Let's make this plus 24 minus 4/3 minus 2 plus 8. And if we combine these all together, it works out to a nice 18. So again, there's a nice picture of the graph, and the reason we did this is because top over bottom, that changed, but right to left always stayed the same. The right was the line, and the left was the... So we were able to do it because we had left minus right was always constant. That's all for this video. We'll see you next class, period.